In this section, we're going to talk about polyhedra. Now, if you remember when we talked about triangles and quadrilaterals and different shapes in the plane, we talked about angles that are determined by those shapes. Now, in this pyramid, I can refer to the angle A, B, C, D. Here's BC, so this is the edge of the angle. It originates up here at this point. It includes this edge, and it includes either this point or this point. You can name it with the E or the D, doesn't matter. You have to have one point in this plane, you're using A, and you need to have one point in this bottom plane. You can use D or you can use E. Now, just as we did with 2 dimensions, you need to remember that the angle is not a subset of the polyhedron. The angle is not part of the polyhedron, but the polyhedron determines a dihedral angle. Okay, so let's look at some polyhedra. Before we classify polyhedra, we're going to just do a quick review on the classifications of quadrilaterals. We have squares, we have rectangles, then parallelograms, a rhombus, plural is rhombi, and trapezoids. We could also have a quadrilateral that doesn't fit into any of those categories. It can just have 4 random sides, but those are quadrilaterals. Now we're going to look at polyhedra. Okay, we're going to look at classifications for hexahedra. Remember that a hexagon has 6 sides, so the prefix hex means 6. So a hexahedra is a 6-sided polyhedra. It can look like this, for example. This is the simplest. It's a cube. It's a regular right rectangular prism. This is a right rectangular prism, and this is just a rectangular prism. Now notice this is not sitting perpendicular to the tabletop. This one is, and this one is. These have this square has right rectangular prism and all the sides are congruent. On this one, the sides are perpendicular and the base is a rectangle instead of a square. This one has a rectangular base. It could be a square as well. The key difference between this one and these two is that these are right, have right angles, they're perpendicular to the base, and this one is oblique. Okay, here are a few definitions. Here's the first one, which is kind of weird. It's a parallelepiped. That includes any hexahedron in which all the faces are parallelograms. Now that would include the 3 that we just looked at. Now the next definition has to do with the diagonal of a hexahedron. It's any segment that joins vertices that do not lie on the same face. And then we can also look at opposite faces of a hexahedron are 2 faces with no common vertices. So let's look at those in the picture and then we'll come back. I've drawn in some red diagonals of a hexahedron. Now notice, this corner has to go opposite this corner. A diagonal of a rectangle would go from one corner over here. But for the solid, this vertex and this vertex cannot lie on any of the same planes. So basically it goes from one corner to the opposite corner. So I've just drawn one, but there's more than one diagonal that you can draw on each polyhedra. Now let's go back to our definitions. Okay, let's read these last definitions and then we'll go look at the pictures. Opposite faces of a hexahedron are 2 faces with no common vertices, and opposite edges are 2 edges that are joined by a diagonal of the parallelepiped. First of all, let's look at opposite faces. If I look at the top of this box and the bottom of this box, those would be considered opposite faces because they don't have any vertices in common. So it would be like the top and the bottom, or the front and the back. Okay, now let's look at opposite edges. Opposite edges would be any 2 edges that are joined by a diagonal. So here's an edge here, and it's joined by this diagonal. If I follow this diagonal, the opposite edge would be this edge right here. So in this case it's the bottom right and the upper left, but those are the opposite edges. Theorem 1016 says opposite edges of a parallelepiped are parallel and congruent. So let's look at opposite edges. Here's an edge, here's its opposite edge. What this theorem says is that what I have drawn here in red are parallel, and they're also congruent. That's true for any opposite edges of a parallelepiped. Because remember, for a parallelepiped, all of the sides and the faces have to be parallelograms. This theorem says that the diagonals of a parallelepiped bisect each other. So that means this length and this length are congruent, and this length and this length are congruent. Okay, this last theorem says that if I have a right rectangular prism, the diagonals are congruent. That means this entire length here is congruent to this entire length here. Now the previous theorem said that they bisected each other, so what is actually true is this and this and this and this. They're all the same length. That's if it's a right rectangular prism. Now it doesn't have to be a cube, it just needs to be a right rectangular prism. Now if you remember, we had a very similar theorem for two-dimensional shapes, quadrilaterals, for these. For example, we know that in a rectangle, the diagonals of a rectangle bisect each other. And if we have a right square, they will actually be congruent as well. And also with a rectangle, the diagonals are congruent and they bisect each other. Alright, just as we kind of shows how the hexahedra are related. Remember that hexahedra are polyhedra with only 6 faces. So look over here. We start with any prism with a quadrilateral base. The quadrilateral can be just some funky four-sided figure. Now, if the faces are all parallelograms, we get a parallelepiped. If the base is rectangular, now it doesn't have to be, it can be oblique, it doesn't have to be right, but if it's just rectangular bases, then we get rectangular prisms. Now, if I straighten up those sides and make them perpendicular to the base, then I get right rectangular prisms. And then in the very center, if I take those right rectangular prisms and actually make all of the faces squares, then I get a cube. Now there is one shape, if you think of what a pentagonal pyramid looks like, it's got a pentagon on its base, and then if you make a pyramid out of it, you can see that it's going to have 5 faces and then the bottom, which makes a 6th face. So it kind of fits onto its own little thing over here. Now, also, besides those pentagonal pyramids, I do have other funky 6-faced figures that would just be kind of floating around in this area right here. They can be hexahedra, but they're not pyramids and they're not any of these prisms. Okay, so look, we got one more thing to look at. It's called Euler's formula. Euler's formula says that V minus E plus F equals 2, where V represents the number of vertices, E represents the number of edges, and F represents the number of faces of a convex polyhedron. So this works for any convex polyhedron. So let's take a look at one. Here we're giving an octagonal prism. So there are 2 octagons here and then 8 lateral faces. So the number of vertices, if you count, there are 1, 2, 3, 4, 5, 6, 7, 8 around the top, and there are 8 around the bottom for a total of 16. If you look at the edges, I've got 8 edges along the top base, I've got 8 edges along the bottom of the base, but then I also have these vertical edges. so there are 8 of those as well. So that actually is going to be 24. And then for the faces, I've got the 2 bases, and then because they each have 8 edges, I'm going to have 8 lateral faces for a total of 10. So if I put it into Euler's formula, 16 minus 24 plus 10 will always equal 2. Before we leave Euler's formula, I just wanted to point something out. If you have a prism like this, and I ask you for V, E, and F, the number of vertices is always going to be 2 times the number of sides of the base. This is an octagon. It has 8 sides, so the number of vertices is going to be 2 times 8, which is 16. The number of edges is going to be 3 times the number of sides of the base, because I've got 3 along the base on the bottom, 3 along the base on the top, and 3 around the lateral edges. So E is going to be 3 times the number of sides of the base. That gives us 24. And then for F, it is always going to be the number of sides in the base plus 2, because 8 will give us the number of lateral sides, and then we'll have to add the top and the bottom. So that will always be 2 plus the number of sides. That's going to be true for any prism. Okay. Okay, so that concludes the day 3 information. In your assignment, there are going to be a number of questions about different kinds of polyhedra, a lot of questions about counting edges, faces, and vertices, and verifying Euler's formula. And if you keep in mind kind of the way that we just did it in that last sample problem, I think you'll be fine. Day 4 and day 5 will be worksheets. I will email those to you shortly. Chapter 10 quiz 1 and 2, and then a cranium cracker worksheet. So those will be coming to you soon, and we'll see you next week.